In this video, we're going to introduce the concept of oscillatory motion. So what do we mean by oscillatory or periodic motion? We mean motion that repeats itself back and forth over the same paths. So let's look at a couple examples. One example, and the one that we're going to concentrate on, is a mass on a spring. So by the way, let's assume here that we have no friction. And we can see that if we take a mass on a spring and we displace the object to the right and let it go, the spring is going to pull that object back towards the equilibrium position. But the mass is actually going to overshoot and go past that. Once it gets over here, the spring, of course, is pushing the other way on the object and pushes it back to the right. And so if there's no friction, this oscillation is going to continue forever. So that's what we mean by oscillatory or periodic motion. Again, you'll notice the mass is just going back and forth over the same path. Another common example that you're familiar with is the concept of a pendulum, that if we take a pendulum and we displace it at some angle and let it go, that pendulum is going to swing back and forth. And if there were no friction there in the pivot, effectively that would go on forever. I want to start out our study of periodic motion by looking at some questions just to help you think about this topic. A mass on a spring is displaced from its equilibrium position by a distance x. The mass is then released and begins to oscillate. The period of oscillation. So first of all, let's define what we mean by period. Period is simply the time for one complete cycle. And by a complete cycle, what we mean is that if I take my mass and I displace it an initial distance x, we know what that mass is going to do. It's going to come up and then it's going to come back down, and it's going to continue that pattern. The time for one complete cycle, meaning the time to go up and come back to the original position, that's the period. So what do you think? Do you think the mass that we hang on the spring is going to affect the period? Go ahead and think about your answer. So it turns out that the mass definitely affects the period. We use capital T to mean period, just like in uniform circular motion. And the next question might be, but how does it depend on the mass? In other words, is the period directly proportional to the mass? Or is it proportional to the mass squared? Or to the square root of the mass? Etc. So that's one of the things that we'd like to figure out in this unit, is how does the period depend on the mass? Let's look at another question. A mass on a spring is displaced from its equilibrium position by a distance x, so same setup, and the mass is now released. Do you think the period of the oscillation depends on that initial displacement? So in other words, whether I pull that mass down a distance x like that, or whether I pull it down a bigger distance, do you think that affects how much time it's going to take for one complete cycle? Well, it turns out it doesn't depend on the initial displacement. And that's surprising to a lot of people, because you'd think naively that if it's got to cover more distance, it will take more time to do that. However, one of the things that we've talked about in a previous video is that the force that a spring exerts is equal to negative kx. So the bigger we displace the spring from equilibrium, the greater the force is trying to get it back towards equilibrium. And that's part of what explains why it is that in fact it doesn't depend on the initial displacement. How about this question? Same setup, except now I'm asking you, do you think it depends on the value of g? So in other words, if I took this exact same setup and I brought it to the moon, or I brought it to Mars, where the acceleration due to gravity is different, do you think that would affect the period of the motion? Well, it turns out that even when we have a mass oscillating vertically on a spring, the value of g does not affect the period. Again, that might not be one that makes sense to you yet, and we'll have to be able to prove that. Finally, do you think the period depends on the spring constant? So in other words, how strong the spring is. Remember that spring constant is what we mean by lowercase k. It has units of newtons per meter. So if I have a stronger spring or a weaker spring, do you think that affects the period? Well, probably you're going to think that it does, and in fact it does. But again, what we want to know is, how does it affect it? So for example, if I have a stronger spring, does it make the period longer, or does it make the period less long? How does the period actually depend on the spring constant? That's another thing that we want to figure out. So it definitely does depend on it. You probably can guess that the stronger the spring, the shorter the period, and that's correct. But it turns out it's not quite as simple as that. By the way, just a quick note. Make sure that in problems where we have both kinetic energy and a spring, remember that lowercase k is spring constant and uppercase K is kinetic energy. All right, so we've come up with a number of questions that we'd like to be able to answer as we go through this unit on simple harmonic motion or oscillatory motion. So let's talk about what has to be there in order to have oscillatory or periodic motion. The key thing that has to be there is we have to have some kind of a restoring force. And by a restoring force, we mean a force that is trying to get the object to go back towards equilibrium. You'll notice that the force that a spring exerts is exactly that. Because as we've talked about in a previous video, if my displacement x is positive, then the force on that object is going to be back towards equilibrium. However, if my displacement of the mass is negative, then the force is going to be to the right. And so the spring is always trying to push the object or pull the object back towards the equilibrium position. However, because the object has mass, it has inertia, and therefore it ends up passing through the equilibrium position, and we get that continuous oscillation that we've talked about. Let's take a look at the following question. As the mass moves from left to right, where is it moving the fastest? So go ahead and pause the video and come up with what you think is the correct answer, and also why it's the correct answer. Okay, so we've asked to figure out where is the object moving the fastest, where is its velocity the greatest as it moves from left to right, so as it's moving in that direction. The answer is it has to occur exactly at the equilibrium position. I want to show you one of the ways you can think about why that is. So let's look at what the force that the spring is exerting looks like as the object moves from its maximum compression to the maximum stretched position, which is going to be over here somewhere. You'll notice that because the displacement is initially negative, the force is initially positive. And in fact, since our formula is F is equal to negative kx, we can see it's going to be a linear graph with a slope of negative k. And so that's what the graph is going to look like. So that's force versus position. Remember, one of the important things we learned when we discussed Newton's second law is that the acceleration and the net force are always in the same direction, and the graphs always look the same because we're just taking the force and dividing by a constant. So the acceleration in this case is going to also look something like this, where the acceleration is positive until right when the object gets to equilibrium, and then the acceleration becomes negative. And that means the object is going to be speeding up until right when it gets to x equals 0, and then at that point it's going to start slowing down. So our maximum velocity will be right at the equilibrium position. Now, one of the things that you'll notice is because the force that a spring exerts depends on the position of the object, the force is not going to be constant as this mass oscillates back and forth. We know that if the force isn't constant, the acceleration isn't constant. And what that means for us is we can't use kinematics. Because remember, those kinematic equations that we derived in an earlier video count on the fact that A is constant. So we can't use kinematics. And that means that we're going to have to figure out a different way to analyze the position, the velocity, and the acceleration of an object moving in periodic motion. Before we finish this introductory video, let's just define some other quantities that are important with periodic motion. The first one is the amplitude. Amplitude, which we abbreviate with the letter A, is the maximum displacement from equilibrium. So you'll notice that when I take this object and I displace at some initial value, that is the amplitude, because that's going to be the maximum displacement from equilibrium. When we let that object go, it's then going to oscillate between A and negative A. So A is the amplitude, and it's the maximum displacement from equilibrium. The period we've already defined. We've said that period is the time to complete one cycle of the motion. Generally, we're going to measure period in seconds. Just like for uniform circular motion, period and frequency are inversely related. So the frequency would be the number of complete cycles per second. And again, for frequency, we use the unit of the hertz. So frequency and period, again, are inversely related. In our next video, we'll look at the details of exactly how does an object in periodic motion move in terms of its position, its velocity, and its acceleration, all as a function of time.